Well, good morning, everyone. We're recording this session. That's why I'm holding the head mic here. The talk today is going to be type wells you can count on, flow regime forecasts. I'm going to talk about more than flow regime forecasts, but that's the main purpose of the talk. My name is Randy Freeborn. I work here at Energy Navigator, and I have special expertise in forecasting and auto forecasting and decline analysis and type wells. It's my passion. That's why I have so much gray hair and I'm still working. And today I want to share with you this new concept on flow regime forecasts. I'm really excited about this concept because I think it's sort of the next groundbreaking piece of information in terms of how we forecast unconventional wells. It's not very complicated, but it takes an epiphany to sort of see it, and that's what I'm going to show you today. As long as my clicker starts working here. Good. So by way of agenda, I want to talk about, first of all, what are the physics of unconventional flow and what kind of things can we build into our decline analysis so that our decline analysis honors those physics. I'm going to show you the modified hyperbolic equation that most people use to forecast unconventional. And the modified hyperbolic equation is nothing more than a two-segment hyperbolic fit. I will show you that the modified hyperbolic can match analytical solutions to unconventional flow. And so it supports our use of that equation pair. Then I'll show you what flow regime forecasting is, how it works, and I'll show you some examples. I'm showing here Montney examples, but I also have some Bakken example to show you. And then conclusions, and then time permitting, I will switch and look at some of the older equations that we have for unconventionals, like the stretched exponential, and a lot of people are using the U modified, and I'll show you some things that you might not have seen related to those equations. So this whole concept of flow regime forecasting, first of all, it's not been published yet, but it is a decline method that I believe honors the physics that we expect to have for unconventional reservoirs. What it does for you is it determines the coefficients for a modified hyperbolic pair of equations. It uses rate versus material balance time as a diagnostic to determine where your flow regimes happen. And oftentimes, that detection will give you an early indication that you're at the end of linear flow and starting to change flow regimes. But most importantly, it's a really simple process. There's 4 logical but separate steps, and as we walk through each of those steps, we determine another coefficient in our modified hyperbolic, or maybe 2 coefficients. What's really important is it's easy to visualize. You can show somebody what you're doing. They can understand it. It makes sense, especially if you're explaining it to a manager or C-suite guy. They can figure out what's going on. So what do we know from physics? I'm showing here a material balance time plot with rate on the y-axis. We use material balance time to identify flow regimes, and material balance time is simply the cumulative production at any point in time divided by the rate at that time. And what we are doing is converting an equation that requires constant pressure into an equation that has variable rate and variable pressure. And so if you think about what material balance time is, it's the time it would take to produce that volume at a constant rate. So that's the transformation that we undergo when we use material balance time. Another feature of using material balance time is that there is a superposition effect going on. So once you move out of out of linear flow and into boundary influenced or boundary dominated flow, the B value collapses to 1. So on material balance time, all the different ARPS hyperbolic solutions all look harmonic. So when we are looking at what the physics are for linear flow, we expect from the equation, the analytical equations for linear flow, we expect to have a half slope when we plot log of rate versus log of material balance time. And you can see that half slope on the graph, and depending on where the data deviates from that half slope, we have two other pieces of information. On the left-hand side, where we deviate, we have something that I call PreLinear Flow. It's where you're cleaning up the well, you're changing the flowing pressure, you're maybe doing some choke management. But in terms of monthly data and just rates, it's data that we can't analyze. We have to throw it away and start analyzing data after that point in time. If we have pressures where we've got the drawdown, we can normalize that rate to drawdown, and that will bring in more of that early time data for analysis. Then after linear flow, we have boundary influenced or boundary dominated flow. So linear flow happens when your fracs aren't talking to each other. So you've got a horizontal well with vertical fracs, and the pressure in between those fracs hasn't changed. The end of linear flow happens when those fracs start to talk to each other and the pressure in the middle starts to decline. So that's the demarcation between the end of linear flow and what we move into boundary influenced. I say boundary influenced because there will be more than one boundary. The boundary may be a pseudo boundary due to other well production, but it will be a boundary, and as all of the boundaries start to affect, so in other words, all of your fractures are communicating with one another, then you are into fully boundary dominated flow. So that's the physics of the problem. What are the equations of the problem? And I know everyone hates math, but I'm going to show you this anyway. If we have a log rate versus log time, that's a power law relationship that gives a straight line. And that's the equation you see on the chart, is the equation for power law. And I'm also showing the equation for a hyperbolic because we want to switch and flip back and forth between a power law equation and a hyperbolic equation. We need to make an approximation for a hyperbolic equation, and it's quite simple. We assume that the BDT term in that equation is really small, and we can ignore it. We still have a problem, though. With the power law equation, we have two unknowns. With the hyperbolic equation, we've got three unknowns. We got too many unknowns to get a straight line using a modified hyperbolic equation. We have to reduce those number of unknowns, and we do that by equating those two equations and solving for one of these terms in terms of a relationship to another one. So we solve for the coefficient, the decline factor, in terms of the other coefficients that we have in our equations. And now we've reduced the hyperbolic equation to two parameters, and we can get a straight line now with our modified hyperbolic equation. So it's more than just saying a hyperbolic equation with a B value of 2 is linear flow. It's not. You also have to make the adjustment on the decline factor. And where you do have a slope of 2, then that reduces to that. So that's kind of all the end of math I'm going to show you in this equation. But it's important if you're going to flip from linear flow to hyperbolic and develop hyperbolic equations that you can use in your software. So here's the issue. If I say I've got monthly data, and I say my maximum QI for my hyperbolic equation is the average rate for that first month, then if you look at the data on this graph, here's the average rate for that first month. That says my hyperbolic equation can never exceed that rate. And so your equation must bend over into an asymptote equal to that rate. The only way you can prevent that from happening is to use your equation and assume a very, very small time. I use a time of something in the order of 1 hour. And using that small time of 1 hour, I calculate the rate at that time and use that rate and time in my linear flow equation, and I can calculate all the parameters. And when you do that, you end up with the yellow line, which gives you the perfect half-slope linear flow equation all the way back to 1 hour. So if you need to work backwards in time, that's one way that you can do it. The other way is to simply say at 1 month, that's my reference time, that's my rate, and that's my decline factor. And any time earlier than that will translate to a negative time. So in this bottom hyperbolic equation, I take the time minus the reference time. So if my time is sooner than that reference time, 1 month, then I will have negative time, and my data will project a perfect half-slope linear flow over the whole period of time. So that's the math to go back and forth between linear flow and a hyperbolic equation. So what I've done is I've talked to David Fulford. David works with Apache in Houston. And David shared with me an analytical solution so that I didn't have to do it myself to a single frac in a closed boundary system. And in purple, you see the analytical solution. We're showing the B value here right now. And you can see that the analytical solution has a transition from a B value of 2, and then it gradually changes down to whatever your terminal B value is, in this case 0. And that's what the analytical solution looks like. But when we use a modified hyperbolic, we're using an instantaneous change in the B value from 2 to 0. So how can a modified hyperbolic equation with an instant change in B value be the same as an analytical solution that has a gradual change in the B value? Well, as we look and compare the answers of the solutions, what I'm showing you here in purple is the analytical rate time solution that we have for this problem. And in white, I'm showing you the modified hyperbolic equation. White and green. Green being the linear flow portion. So we can model the physical observations using both of these equations, and they overlay each other. So how can that happen? The answer is that in linear flow, you don't require that the B value be a constant or that it have a transition. The equations dictate that the product of the B value, the decline at any specific point in time, and that time is equal to 1. So in the analytical transition, we have the B value changing over time. And in the hyperbolic equation, the B value is distinct, but the decline factor is changing so that you end up with the same results no matter which equation you use. So the important part is that the product of B dt is equal to 1. And so for those things happening, for the transition period where the analytical solution has a lower value of B, it must have a higher value of decline parameter. And that's why you can use a modified hyperbolic equation to model unconventional production. So now let's come to this new method of flow regime forecasting. I said there were 4 distinct simple steps. The first step is using a rate versus material balance time plot. And we need to position, then we need to find out where that half slope is. And so that's our first step, is to find out where that half slope is. The second step is we change where the end of linear flow happens in a trial and error basis until we match the whole PreLinear or linear flow and boundary dominated flow data on a material balance time plot. What that does is gives us a window of knowing where linear flow happens. Then we switch to rate time. And in rate time, we do a log-log fit of the data within linear flow. And that gives us all the coefficients that we need for rate time to figure out our hyperbolic equation. And then we finish that by finding the b-value for the post-linear flow period. So let's look at this now one step at a time graphically. So step 1, we need to find out where linear flow is. Linear flow has 2 parameters, and we already know one of them because it's a half slope. And so all we need to do is find out where the other coefficient is, the intercept, so that we line up with the data. And so that's what we do. We keep guessing until we line up with the linear flow data on our rate material balance time plot. And from that, we look for where the data deviates from the half slope in the early time. And that tells us where the start of linear flow is. We don't know where the end of linear flow is, but what we do know is at the demarcation between linear flow and post-linear flow, the rates are the same, the decline factors are the same, and we know that post-linear flow, the b-value is 1 when we plot on material balance time. The only thing we don't know is where is the end of linear flow. It could be that we haven't reached the end of linear flow yet. And for this data, that would cause us to have our equations higher than the data. And so maybe the end of linear flow is sooner than that. Or the end of linear flow could be imminent, in which case our equations are giving us too low a rate. We know it's somewhere in between, and we can do a trial and error solution to line up all the data on our material balance time plot. We've now identified where linear flow happens and where our two flow regimes occur. Now, when I do this plot, if I change from material balance time to time, that window that you see, those purple bars that you see, will not change. Linear flow is still in the same position no matter what I do with the x-axis. So that's what I'm going to do. I'm going to switch to next step 3 and switch material balance time on the x-axis to time. Now there looks like there was a slight shift there simply because the scaling on the graphs is different. But that purple bar where linear flow is hasn't changed. With this method, I need to make one assumption. The assumption is that we still have a power law relationship, log rate versus log time, when we're using calendar time instead of material balance time. If I make that assumption, then I can do a best fit, a best straight line fit of the data that's in the linear flow window. And from that, I can determine all of the coefficients that I need for linear flow using those long equations that I showed you in the first few slides. So now I have the math for the first segment of my modified hyperbolic equation. Then I move to step, there's sort of one other, no, I'll come back to that. So now we switch to the fourth step. We now know all the parameters for linear flow on rate time. We know where the end of linear flow is, and we know at that point the rates on either side have to be the same. The decline factors have to be the same. We just don't know the b-value. And so we can try different parameters for b-value. We know that in the post that b-value ought to be limited from 0 to 1 because now we're into boundary dominated flow and we're into ARP's rules for the legitimate b-values. So I'm showing you here a b-value of 0. There's a b-value of 1. The real b-value is somewhere in between. I would trial and error this, and I've trial and errored, and the best fit that I can see is a b-value of 0.6. We now have all the parameters that we need for a modified hyperbolic equation. We've done it very simply, step by step by step, and it's just so cool. What it's done when we use material balance before, the issue or the problem we have is once I get a fit against material balance time, how do I convert that back to rate time? It can't be done. This allows you to do it. This takes you that one step that leads you from a solution of the rate material balance time equation back to a rate time equation. Now I'm going to show you the data for both curves together, the material balance time and rate time. I'm showing you where the linear flow window is on this data. But the first observation that is really interesting is that the slope of these two equations is not the same. So for all of you that use diagnostic plots of rate time to find where your linear flow period is, where your half slope is, you're probably making an error. Why does this happen? I don't know the answer to that, but from the data I've looked at, I think it's a multi-phase effect that's going on. My observation is that that white line becomes steeper as your product mix becomes oilier. And that's why if you look at, I have the opportunity to look at a lot of US data, and the first question I had when I looked at Niobrara data was, all this data looks like it's harmonic. How can it be harmonic if I'm in linear flow? And I think this is part of the answer. When you get lower b-values that are, when you fit your rate time and it looks like it's 1.2 or 1.3, I think this is the reason why, but it also says you need to use more complex diagnostics to do your fitting. The other thing that comes out of this is if we're looking for a lot of people use a diagnostic of 1 over rate versus square root of time. How many do that? None of you. Oh, I see Vincent nodding. So when you use 1 over rate versus square root of time, you're making an assumption that you have a half slope. But we no longer have a half slope on our rate versus time plot. Linear flow is a b-value that's less than 2. And so when we do square root of time on that diagnostic, it shouldn't be square root of time. It should be the 1 over b root of time. And so that's one piece of information that comes out of this. Also look at where the end of linear flow is on this plot. And look at, if you were looking at this data and looking for a deviation to find out where the end of linear flow is, it would be very, very difficult to see. But when you're doing this mathematically, you only need to see a slight deviation on the data, maybe 2 or 3 or 4 months of data, and you can tell where that end of linear flow is. And it actually looks like it's in the linear flow period. It's actually earlier than you might normally expect. So let's take this one step further. What if we are doing an evaluation and we're using rate versus time to figure out where linear flow is? That's what this example is. I'm now plotting rate versus time, and I'm finding my half slope. And look where I picked the linear flow window on this. And let's now compare. This is the same example. Now let's compare the window that we had before. And you can see how different our linear flow window is on one chart, on one versus the other. The impact of that is that we're picking the end of linear flow too early when we use rate time. And because it's too early, our limiting decline is too high, so we're switching to an exponential at too soon, or exponential or low b value at too low a time. And I'm stating the EUR here, but let's look at this same data in terms of EUR. So in purple is the fit we get looking for linear flow using rate versus time, and the yellow is what we would obtain using rate versus material balance time. And in this case, there's a 48% difference in the remaining EUR. Now this is an old well. It's the earliest Barnett Shale horizontal well. So I got 14 years of data on this. So in terms of ultimate recovery, that difference isn't very great. But you can see the effect of using rate time to find the end of linear flow. The other thing that we can do is we just use ValNav and click do the best fit. And that's what I've done here. So the purple line is just sort of a best hyperbolic fit of all the data without taking the time to figure out where the flow regime is that you need to work with. And we have an awesome fit. That works great. I've used a delim of 4% on this, and I've done that because I'm already at 4.5%, and so I'm just giving it a little more time. There's our linear flow window, and there's the forecast that we would obtain by using material balance time to properly identify the flow regimes. Here there's a difference. The difference is about 15%. So based on this one example, you're probably not going to be as wrong by just doing an auto fit or a best fit of the data using your judgment. But I think you're going to end up with the right result by plotting your data up on log material balance time, and then using that, or just using where you see the deviation to pick where the end of linear flow is, so you know if you're past linear flow, what data to fit. If you haven't hit linear flow yet, maybe you ignore the first 6 months or year of data in that fit, just to make sure that you've ruled out all that pre-linear flow data and you aren't getting the wrong answer. One thing I didn't mention when you're using material balance time is that all of the data collapses to 1. And if you have bad data, spikes, it also appears on that half slope line. Now, this is a log-log plot, so even though this is a half slope line, or we've got exponential, you don't sort of really see it as a half slope until much further. But what you can see is this data here. I'll use a pointer so those on WebEx can see. This data here is fitting perfectly on the unit slope line, and yet it's data that doesn't fit the rest of the trend. But it looks like good data, and I've been following this data every 2 or 3 months, and it's still fitting on that lower trend. So what's happening on this well? I think, because this is an Elm Coulee Bakken well in North Dakota. I don't know what's happening here because I'm just pulling public data. But I think what's happening is that there's some damage on this well. Maybe there's some leaking tubing, maybe there's some plugging, maybe there's some scaling, but there's some damage here that for whatever reason the operator has not yet got to this well to repair. And if that's the correct assumption, then you need to shift and use the old data to project what this well might do if you were to give it a workover and clean up the damage. If you're not going to do that, then you'd use the dashed line, and say, you know, there is some damage here. Maybe I would just fit that dashed line all by itself with just a simple ARPS fit. And that's the situation you get if you chose not to go in and repair this well. Big assumptions on my part because I don't know the well and I don't work with it, but that's what I see looking at the data from an outsider looking in. So I'm going to show you a few examples, Bakken, Eagleford, and Utica, and these are based on daily production data, and I'm doing that because I want to make a point with respect to daily data, because everybody thinks that daily data is great. It's the only thing that you should use, and I want to show you that maybe there's a balance between monthly and daily data. So here's my daily data, and from my experience looking at daily data, and I frankly don't get to see a lot of daily data, this to me looks like really good data. If I look at the information on this plot, I see a couple of things happening. In early time, I've got lower rates, and then I get a bump in rates. For this data, I know that this is flowing data. Then they installed a pump jack, and we've got a pump jack coming on through this data here. And then you can see I'm plotting 1+ water-oil ratio on the bottom, and look what happens to the water-oil ratio. This well has watered out, or is watering out, and it's changed the recovery mechanism. We're no longer into a normal boundary-dominated flow. We're into a water coning environment, and so we end up with much different performance. So I'm going to break this well up into separate segments and let you look at each segment. So here's the flowing segment only. And using only this data, I'm actually seeing some bend in the data in history. And remember I said it's hard to see where that is. I'm using monthly data to figure that and rolling it back into here. But there's the recovery that I would expect from this well using daily and monthly data. So 340,000 barrels, 307,000 barrels. I'm going to show you the same plot now. Instead of daily, here's the monthly data. Look how much cleaner that data is. It really does make a difference. Now, monthly data limits the number of data points I've got. So here's what I recommend. A lot of people just use a monthly rolling average of their data and just use a rolling average of their daily data, and that's what they use. The problem with that is as you pass demarcation points, you don't get to see that. That demarcation is just smooth. It's not smoothed away, it's smeared and spreads it. My thinking is, and I've done some examples with this, instead of taking your daily data and merging it into to create monthly, why not merge it into 5-day increments or 10-day increments? And then you only have data between 2 points that will be smeared, but you'll actually see the individual points. And as you run this data through 5 or 7 or 9-day data, you get very good smoothing. You get much more clarity in your data. And that's where I'm leaning to in terms of a recommendation. But look how clear this is, and that's where I get the 307,000 barrels. So now we're into pumping data. And using the pumping data, I end up with a solution of, whoop, I'm not sure what happened there, but using the pumping data, I end up with 410,000 barrels and 497,000, depending on which data I use. It's in the right direction. We've added a pump. We ought to see more recovery. There's the daily data or the monthly data that we see for that well. Again, it's just so much clearer to see what's happening. So here's my issue. If I use daily data and I try to make inferences on the first 30 or 60 or 90 days of data, I'm not sure that I'm even in linear flow yet. Now, I asked David Anderson with Anderson Thompson how much data daily data do you need to be able to use RTA to get a good answer? And he says, well, they can do something with 90 days, but more data is better. So there's a risk of starting to do projections with daily data until you've got more. And then if you actually do some smoothing of that data, maybe you can use this analysis instead. So now I'm going to switch from pumping data to this data that's into a water coning mode. I cannot match this data in any way at all. I can draw a line through material balance time. I can't really do anything with the rate time. And so in this case, I go back to forecasting 1+ water-oil ratio versus cumulative oil production. Those of you that use ValNav will have seen that. If you haven't seen that, this is equivalent to plotting oil cut versus cum oil. It's what Brad and I used to use in Suffield to predict production there. The next example is Eagleford. Now this is monthly data, and so you can see, again, you can very clearly pick out all of the steps and stages that I described in the initial 4 steps of how this equation works. And this is another Eagleford well, the same thing. In this case, we have a problem. And the problem is we have no data in linear flow, either rate time or rate material balance time. So now what do we do? But we've got post-linear flow. So I can fit, I know I'm post-linear flow, so I can fit this data here that's post-linear flow using ARPS, and I can make an estimate of where the end of linear flow is. And based on the estimate I make, that projection then will move backwards in a straight line. So the further down the curve I go, the steeper that line will be. The further across the curve, the shallower it will be. And it lets me figure out an estimate of where that line ought to be. Now, why do I care? I've already got boundary dominated flow. I don't really need to worry about linear flow. And the answer is you care because you want to gather all the end of linear flow information you can so that you've got some way to make a judgment on where end of linear flow will happen on all the wells that haven't reached linear flow yet. So that's the reason why it's important and why you want to do both sides of the analysis. Sometimes it won't work, but it's the kind of valuable information that you need. And then the next well that I'm showing you is a Utica well. Again, daily data merged into monthly. You can see how clear this is. We've definitely not reached the end of linear flow, so we need to make some assumptions. For this plot, I've assumed a 20% nominal terminal decline. Now I want to show you a couple of Montney examples because we're in Montney country. So here's another perfect example. I've got lots of data in both flow regimes. I can fit. You can see how well this method works for Montney. Notice the end of linear flow on rate time is 35% decline. I'm betting that no one in this room would ever, that's familiar with Montney, would ever dream of a 35% terminal decline for Montney, but it's pretty clear from the data on this well that that's what this well is saying. How do you end up with such a high limiting decline factor? Well, you start going from 20 fracs in a well to 50 or 60 fracs in a well. End of linear flow happens much sooner. Because it happens sooner, it's at a steeper slope. This is another Montney. Both of these Montney wells are in Swan, and they're gas wells. In this case, I can do a good job on rate material balance time, but I have no data in the linear flow period using rate time. So again, I have to go back to the fallback. I need to fit my boundary dominated time or post-linear flow time, and then make it, I know where the end of linear flow is, and that's going to give me the projection upwards for the rate time plot. Now in this case, why would I be interested in that? It's more than just where is the end of linear flow. I also might want to know what is the B value for my linear flow period so that I can use that in combination with other wells to make some judgments for new wells that I might drill, or wells that might not have enough data to forecast. Switching to Montney oil now, and I can't remember where this is, but it's on the Alberta side, and it's north of Kakwa. And so here, again, showing that we have data in both sides to analyze this data. But look how early the end of linear flow is happening. It's under a year, or maybe it's 1.5 years, something like that. So as you have oil, the equation that if you've attended Dr. Lee's course at all on forecasting unconventionals, he'll show you an equation for the end of linear flow. And on the bottom of that is permeability, and the top is the distance between fractures squared. If we have an oil reservoir, we have to have higher permeability than gas. So we have to have the end of linear flow happening much earlier, and it would be in proportion to the permeability. So maybe the difference in permeability might be 5-fold between gas or oil, or 5 to 10-fold. And so you might expect that fold of change in time for the end of linear flow. So this next equation, or next well, also an oil well, has a workover in it. So if you look at the data carefully, and I think I just skipped to a previous slide. If you look at the data carefully, you'll see that we come down and the rates fall off, and then the rates increase. And so you can also, or the rates come down here, and then we get a bump and the rates increase and then they fall off. Bob Bachman, if you've listened to any of his talks, suggests that when you plot material balance time, if your data on material balance time doesn't return to the original trend, then probably that's an indication that you're getting incremental recovery. And so it looks like we're getting incremental recovery from this apparent workover. How would we handle it? What I have done before is I've said, well, I'll take my rate time profile and I'll shift it to line up with the real data. And so when I do that, I'm lining it up with this early time data here. Is it predictive? No, it's not predictive. It's not telling me if I actually used this data here, and I think that's my next slide. No, if I actually use the data up in here to predict, I don't get the right forecast. So shifting the data up, in this case, isn't going to give me a good indication of productivity. The other alternative is, what if I reset my material balance time calculation to start at just past the workover? And if I do that, I get, oh sorry, let me backtrack. I'm just going to fit the post-material balance time data and run through this data. And so is it predictive? Well, what I can do is isolate the first 4 or 5 data points and predict using those 4 or 5 data points. And when I do and project it forward, I am predicting the data fairly well. So those are the choices you have. In this case, I've only done one test of this, and I don't know if it works, and I would not take this to the bank because I've tried it both ways for lots of different wells, and sometimes it works and sometimes it doesn't. So I'm not comfortable with saying that that is the way to go, but I am comfortable in saying what I used to do probably is not a good approach. I'm going to wrap up flow regime forecasting, then I'll get to chat some more. So what I've shown you is a way to create modified hyperbolic coefficients that integrates the physics in the sense that you're honoring flow regimes, and that's a good thing. I've shown you vaguely that the end of linear flow can be detected maybe a little earlier using this method. We've seen that there is a fixed window for linear flow, and that doesn't change, and that allows us to link rate material balance time to rate time. And I've shown you that the usual diagnostic that uses 1 over rate versus square root of time may not give you the right answers. And, of course, bad data fits on the unit slope line, so that's a really good way to help find out where some of your bad data is and rule it out. So I'm going to switch topics now a little bit and talk about the stretched exponential equation that's been around for probably 15 or 20 years now, and give you some thoughts on that, not so much in terms of dealing with the stretched exponential equation, but you can sort of use the logic to think about other equations that you might see in the literature. So here's the equations. Again, some more math. You thought you were going to get away and not have any more math. So the top is the stretched exponential equation. Usually it's expressed in a variable called tau, because to get Cume production, you need tau to calculate gamma functions to calculate the Cumes. But I'm not worried about that, so I've simplified the format of the equation. If we take the log of both sides, we end up with this. And if we make a simple transformation, if I knew the value for n, and n is not b in the stretched exponential equation, in fact, it's the opposite. N of 1 in stretched exponential is an exponential equation, and n of 0 is a harmonic. And so if I make the simple assumption that t prime is t to the power n, and I guess what the value of n is, I end up with the equation of a log-log, or an exponential equation, which is a straight line. So if I guess the right value of n, I'll get a straight line. And if I don't get the right value of n, I won't get a straight line. I'm showing the b value just for interest if you look at these slides later. The advantage that people said the stretched exponential equation had, first of all, the b value changes over time. Is that important or not? We'll look at that. Secondly, it's based on an infinite number of exponential solutions. So there's some theoretical basis to the stretched exponential as an infinite number of, summing an infinite number of exponential equations. And finally, the advantage that everybody liked is it curved down at the end. Some said, oh, it's predicting the end of linear flow, which it can't possibly do. Others said, well, it's just a conservative answer, so that's a better number to use. So that's why people wanted to use the stretched exponential equation. So let's go back to Fulford's analytical equation for linear flow, and well, linear and boundary dominated flow. So I'll take that analytical solution and I'll start that analytical solution using 1 hour of data. So there's 1 hour of data, and the red line is the 1 hour of data. And I will fit that full set of analytical data using a hyperbolic equation. And the fit that I get is the white line. So we end up with that asymptote problem. To get the right fit here, I have to assume a QI, or an initial rate, that's lower than it should be, and that asymptote says in early time I don't get a fit. And look at the b-value. The b-value is continuously changing. That's not what we expect in the physics. So when people said this is a good equation because b-value is changing, that's only half the story. It needs to change in the right way, and this isn't. So now I'm going to take that same analytical solution, but I'm going to start fitting it at 30 days instead. So I start fitting here, and now I can fit the data really well, and I can fit more of the data than I would before. If I extrapolated that backward, I would get a better fit. But now my best fit is an exponential equation. In other words, I've moved past the end of linear flow, and now I'm fitting exponential. So how would I solve this equation? So this is the same slide as before, but with different stuff grayed out. So the way I solve the equation is I just guess a whole bunch of values of n and plot it up and see which one gives me the least error, because it's really hard to find a straight line on some data. So when I do that, that's the error that I get in the rate data versus the value for n that I choose. And now I can very easily go to this graph and pick off the right answer. And so that's the easy way to solve this. You could put this into a solution technique, but you get a great solution for the rate, and you're not having to make assumptions that the authors originally made in the equation, and that's assume that the highest rate you saw is the initial rate, which means you got an asymptote in the wrong place. So how does this work? So I've taken all the data from this other well that I've been working with, and the white line is the best stretched exponential fit of the data that we have. And the red line is the fit that I would get using this flow regime method that I've just showed you. And yellow's the b-value. So now the b-value has some curvature when I'm fitting the right data, but it's still curving over the whole time period. It's not doing what we expect of the physics. But I get a fit of the data in early time, and I project that forward in late time. So that's what I get. What would happen if I ignored all this early time data, which I've said is PreLinear Flow data? And what if I just use the linear flow portion of this data to do a fit with the stretched exponential equation? When I do that, I get a straight line that's equal to linear flow forever. So the stretched exponential, if you're in linear flow, will project linear flow forever. So obviously, it can't predict the end of linear flow. So why does it curve over? The reason it curves over is because we're fitting a curve in the data. So if we're including this early data that really shouldn't be fit because it's PreLinear Flow, we've introduced some curvature to our fit. And that curvature has to project into the future forecast as well. So the reason the stretched exponential curves down at the end is because you've included, I won't call it bad data in the sense that it's real data, but it's data that's been influenced by operational changes that the operator's done in producing the well. And so if there's no meaningful reason for that curvature, then I don't feel comfortable using that to predict how a well will perform. And so then the next question is, what if I include linear flow and post-linear flow data and do the stretched exponential? And when I do that, I get the curve in yellow, which is still higher than it should be. And the reason it's higher than it should be is because we're looking at a log scale. So even though we have a lot of data in post-linear flow time, it's compressed because we're looking at a log plot. And so it has less weighting than it should have, even though it extends over a long period of time. And so the recommended solution is just fit the linear flow data, find out where linear flow data is, and just fit the linear flow data, and then add a terminal decline, that the same as we add terminal declines to hyperbolics. In which case, where's the advantage of the stretched exponential? Why don't we just use a modified hyperbolic? So the next equation I want to show you is the U-modified stretched exponential equation. There's hardly a university paper that compares different equations that doesn't look at the U-modified. And so I want to spend a minute showing you this because it's really interesting. U takes a different approach. He starts with the same equation, but he says, I'm going to take the log of both sides, and then if I log something long enough, I'll get a straight line. So he takes log again of both sides and says, oh, now I have the equation of a straight line, and that equation of the straight line will give me the value for n, and the slope will give me the value for the decline factor. And so that's his special plot. He makes an assumption that the maximum rate, or the QI, is the maximum rate observed anywhere in history. And we've seen what happens when you do that, but let me show you that again. One of the beauties of this is it's a direct solution. There's no iteration to get the answer. It automatically discards PreLinear Flow data, and I'll show you why that happens. And it does give you a better estimate than SEPD. So in yellow, I'm plotting his specialized plot. So remember, the data has an asymptote, and the initial rate can't go any higher than that initial rate that you specify. And so by saying the initial rate is the maximum I've observed in time, means that this graph has to curve over to that asymptote. It can't go any higher. And to make that happen, this line has to fall in earlier than the data. And when it falls in earlier than the data, this data in the specialized plot says you ought to ignore it because we're looking for a straight line on this specialized plot. So by using that maximum rate that you've achieved as being the initial rate for your stretched exponential, he's automatically rejecting that early data that ought to be rejected in the first place. And so he's solving one of the problems associated with the stretched exponential equation. And so here's clearly showing that asymptote that I was talking about. Here's the real data, and if this is the maximum rate observed, there's the asymptote, and the data has to curve over to meet that asymptote. It's really quite unique. It's not by design, but that's why his equation, or one of the reasons why his equation seems to work. And so if I choose different values of that QI, if I say, let's not pick the maximum rate that was observed, let's pick the real maximum or a different number, you can see that as I increase the maximum rate from 700 to 1400 to 3000, I extend the time that I have, the amount of data that fits on the straight line. In Yu's publication, he said his specialized plot is really telling you where linear flow is. And to a certain extent it is, but if I say I'll pick a different Q, then I have a different linear flow period. So having said all of that, how well does it work? His equation is shown in white, and I'm comparing it with the flow regime equation. And he's getting virtually the same equation, the same fit that I would get using the flow regime equation. And so my response is, I've only tested this on a few wells, but my response would be, don't throw out the U-modified equation until you've had a chance to test it, because despite the assumptions that are being made in the equation, he's making some self-corrections that ought to be made, and he's getting much better results than you'd get except using the flow regime equations. So that's the end of my time, or end of time and still leaving a couple of minutes for questions. And so I won't say any more other than where do we fit with the flow equation or the regime forecasting. It's something we're working to put into our model. It will probably be put in first as a manual exercise, which will still be very fast, 10 or 15 or 20 seconds, you'll be able to forecast a well. But we're also trying to automate the process so that you'll get a first estimate, and maybe 80% of the wells will be right, and 20% you'll have to tweak by hand. So we're trying to find a way to increase your productivity, and that's the process we're in now. So why don't I open the floor for questions? Let's say we've got about 5 minutes for questions and see what people think.
Randy, I did receive one question from online, so I'm going to read this out and hopefully I make sense of it, and I don't misinterpret it. So it's slides 17 and 19. Just to confirm, the assumption here is that we are ignoring early production fit/match or PreLinear flow, but trust more the linear flow and transition to nonlinear flow for forecasting.
That's the objective of the flow regime forecast. But what you're seeing on this slide 17 and slide 19 is that we're including all of the data.
Okay.
If we included less than the data, we would get a different answer. So I'm trying to replicate what people are doing today as to what, rather than what they should be doing. If you have two sets of flow regimes and you're using ValNav right now, then clearly you just want to fit the second flow regime. Because if you try and fit data that blends through two, you're just going to get garbage.
So this person says, in reality, yes, this makes sense. However, for EUR, do we adjust for the mismatch in early production? And I think his example is material balance time-based EUR always greater than CD time-based EUR.
Well, I'm not sure that material balance, if you're talking about a flowing material balance time, then I'm not sure it matters either way, because you're still projecting the data. The prior cumes are prior cumes, they don't change. So all you're doing is reflecting the cume from your last production date forward. And so the prior cumes don't influence what your EUR would be for the well. Well, if that concludes the questions, thanks for coming. Send me an email if you think what we're doing is a great idea, and that'll influence my bonus, so that's a good thing. Thanks for coming. See you later.